Based on extensive measurement data and manufacturer specifications, a calculation software has been developed to enable the predictive calculation of the transient charging and discharging behavior of thermal hybrid energy storage systems. Using this calculation program, it is possible to calculate and dimension hybrid thermal energy storage systems based on PCM objects in terms of performance and energy on a project-specific basis. The program is currently in a beta release stage and is continuously being developed. As the simulation foundations of this program allow extrapolation to any unvalidated storage systems, no guarantee or liability is assumed for damages arising directly or indirectly from the application of this demo. At the University of Applied Sciences Münster, extensive laboratory investigations were conducted with various phase change materials in different PCM objects. The data obtained from these experiments serve as a foundation database for calculation parameters within the calculation algorithm of the software. Renewable energies are primarily generated in the form of electricity. Therefore, when considering energy storage, one naturally thinks of electric storage first. However, if you consider that a significant portion of overall primary energy demand is used for heating and air conditioning in our residential, non-residential buildings and industrial processes, thermal storage often makes more sense. Let's first take a look at our renewable energy sources. Wind and photovoltaically generated electricity is volatile and often occurs outside of normal usage hours. It would be beneficial if this energy could be stored for later thermal use. Similarly, unpredictable is the demand side. The demand for heating, cooling, and domestic hot water or thermal process energy often distributes stochastically throughout the day. When cumulating the energy demand, ideally the cumulated stored renewable energy meets the demand. Now a system is sought that efficiently converts the renewable electricity into heat and cold. The compression refrigeration machine, also known as heat pump, is the ideal choice here, providing both. The challenge lies in the required large storage and the decreasing efficiency of the machine with storage temperature. By upgrading the storage with phase change materials, they become much smaller, as the storage capacity can be almost tripled depending on the application. Since PCM can absorb very large amounts of the thermal energy during the phase change at a constant temperature, the efficiency of the compression refrigeration machine increases again. If this system is integrated into residential, non-residential buildings or production processes, it allows the direct storage of locally, regionally, or nationally generated renewable energy in the thermal storage system through external control, such as that of an energy supply company. This enables the buildings or processes to heat and cool autonomously over a defined period. The left image area shows the hydraulic system of the experimental setup where various PCM objects with different PCM were investigated. In the upper center of the image, the current configuration from the laboratory experiment is visible. As seen in the other pictures, real projects based on these principles are already built. In the right diagram, an experimental course of the system can be observed. In the right diagram, the lower blue line represents the storage inlet temperature into a storage heated to 67 degrees, fully filled with PCM objects. The red line shows the storage outlet temperature as a step response. The phase transition is clearly visible and in this example the undercooling of the PCM can be observed. All PCM data stored in the program database for simulations adheres to the specifications of the RAL Quality Association. The phase transition temperatures and the precise enthalpies of phase transitions were represented in accordance with the RAL Quality Mark 896. For more information, visit the homepage of the RAL Quality Association.